Okay, so yeah, good evening everyone. Yeah, so good evening and yeah, welcome to the week 5 live session course on fundamentals of protein chemistry, which is being taught by Professor Shagota Dasgupta of IIT Kharagpur. I am Srijan Sen and today I will be taking the week 5 live session, right? So we have few people who are joining or yet to join. Okay. But that's fine. We will start with the class anyway. So like I will be first talking about the lecture in brief and then we will solve a few question and answers. Right. So I'm sharing my slides with you all. Okay, so I hope my screen is visible to you all. Right then? Okay. That's great. So let us start with the class. So previously we talked about, in the previous classes we discussed about proteins, a lot about proteins, about protein purification, but we need to know a little bit about the applications of proteins. So one major thing about proteins is that proteins are simply not functional inside our body. It has to do some kind of activity, and also from this activity proteins have a tendency also to have a lot of interactions, like protein-protein interactions, protein peptide interactions, protein nucleic acid interactions and all. So with this thing in mind, we will talk today about protein-ligand interactions. So let's understand a little bit about the binding of ligands to the macromolecules. So in the 25th anniversary of the Institute of Molecular Biology that was held at the University of Oregon, uh, a famous scientist named Linus Pauling, you all must be knowing about him, he said, the secret of life is the molecular recognition, that is the ability of one molecule to recognize another through weak bonding interactions. So here the concept of the ability of proteins to undergo ligand interactions or interactions with other macromolecules comes into the concept. Right, so if we believe this thing, so we need to know that binding is the first step that is necessary for any biological response. So proteins are there, some macromolecules are there inside our body, so they need to interact to carry out a particular function. We have seen a lot of signaling molecules, signaling pathways. We have studied about a lot of them, and all of them involves the interaction of one moiety with the other. And from here, so most of them belongs to the proteins. They can be a signaling proteins, they can be a cascade proteins, and so on and so forth. So therefore, so the interaction or the binding is a very necessary step or a very key step in any biological response process. Now, before the molecules can perform a function, they must interact with a specific ligand. That can be your nucleic acid, that can be like the transcription factors, that can be peptides, that can be other protein molecules. Like things happen, so many things happen inside the cell. Some misleading protein-protein interactions can lead to a certain kinds of human pathologies. Now, to understand the binding, we must consider the equilibria involved, how binding is affected by the ligand and the macromolecule concentration, and how to experimentally analyze and interpret the binding data and binding curve. Just the binding is not very important. We also need to undergo a lot of analysis to get an idea about everything, like whether it's a weak interaction or a strong interaction, how well they're interacting, informations about the binding site, and all these informations do matter to us. And we need to keep in mind that one of the property or a characteristic feature of binding should be, like it is essential, but it should be like the specificity of ligands and the binding site should be such that there is a reversible binding among the ligands and the protein that it is interacting with. Now, based on the types of binding, we can categorize them as an induced fit binding or cooperativity binding. Now, both of them operate in different ways. but more or less we need to understand about the binding to get an idea about whether it's an induced fit model or a cooperativity model. Now that is more important to us. So interactions and these interactions can be regulated as well. So how does this interaction work? It is the reversible transient process of chemical equilibrium. Like A plus B is in equilibrium with AB. Now, a molecule that binds a protein is known as a ligand. That is a small molecule, not necessarily a small molecule, but probably a small molecule which we call as a ligand. This ligand can be your carbohydrates, can be other peptides, other proteins, small molecules, or even nucleic acids. So there can be wide range of ligands, not necessarily small molecules only. Now, a region in the protein where the ligands bind is known as the binding site. The ligands bind via non-covalent forces that dictates the protein structure sometimes. So the folding upon binding, so like the function, some proteins becomes very functional after with the help of some partner proteins. So these partner proteins helps these proteins to fold, and that actually leads to the increased functionality of that particular protein. Now, this binding can be understood as a quantitative description where in a ligand that binds reversibly to the site in a protein, like you have a protein, you have a ligand, and when the ligand binds to the protein, it's the Ka or the association constant. When there is a dissociation, and the reversible pathway is called the dissociation constant or the Kd. Like when the PL, the complex molecule, breaks, we call it as the Kd. Now the kinetics of such a process is described by the association rate constant or the dissociation rate constant. Now after some time, what happens, the process will reach the equilibrium where the association and the dissociation rates are equal, like Ka into protein concentration into ligand concentration, which is equal to Kd, that is of the ligand. Now when we compare the equilibrium composition, we can frame a formula like Ka, that is equal to your association constant by the dissociation constant, which is equal to the concentration of the protein ligand complex divided by the protein concentration and the ligand concentration. When we analyze it in terms of the bound fraction, like how many molecules of ligand have bound to the protein, or what is the fraction of this complex mixture, like a protein ligand complex, we can frame a formula where theta is the fractions of occupied binding sites, which is equal to your protein ligand concentration divided by the protein ligand concentration plus the protein concentration. That is the total protein concentration in the entire system or the entire reaction. And based on that, the bound fraction or the fraction of occupied binding sites, that is a theta, can be simply written as ligand concentration divided by ligand concentration plus Kd. What is this Kd? Kd is the dissociation constant. What does it represent, or what is the significance of Kd? Kd is gives you an idea about the how tighter or how strong your binding is. For example, if a Kd is in a millimolar range, we call it a weak binding. So higher the Kd value, lower is the binding affinity, and lower the Kd value, like in nanomolar, picomolar, higher is the binding affinity. So lower Kd indicates better binding. Now we can plot a graph of theta versus ligand concentration, and at that particular point where 50% of the ligands are in a bound state, that is theta equals to 0.5, we can tell that that is our Kd value. So 50% binding of the ligand to the protein is where we calculate it as Kd. Now, there are different ways of plotting the graphs. We don't need to go into a lot of details about this, but why is it important is because if you know the ligand concentration, if you know the complex concentration, you can plot a graph of uh, complex concentration divided by the ligand concentration in the y-axis and the complex concentration in the x-axis, you will get an inverted straight line, and from this inverted straight line you get a slope of -1 by kd. So if you are aware of the PL, the complex concentration and the ligand concentration, it will easily give you the kd value, or from there you can calculate the kd. But mostly from this particular graph, we are able to get the kd at a much accurate, with a much higher accuracy. Now, just as I was saying, the thermodynamic connections, what is the thermodynamic connection of this particular binding? So it is like, so the interaction strength, because we talk about binding in terms of Kd, or the dissociation constant. So we need to understand that the interaction strength can be expressed as association constant in units molar inverse, dissociation constant Kd in units molar, that is Kd equals to 1 by Ka, and the binding free energy, that is also very important, that is delta G naught in kilojoules or kilocals per mole. Now, it is not very difficult to calculate delta G from a known Kd or a known Ka, because there is, you know about the Gibbs free energy, that is delta G equals to delta H minus T delta S. Also, it is relatable, like delta G equals to minus RTL and Ka, or RTL and Kd. And from there, you can get an idea about the Gibbs free energy or the delta G. You can get an idea about the Kd, and that will help you to also give an information about the strength of the binding, whether it's a weak binding or a strong binding. So what do we call a stronger binding? If the Kd value is less than 10 nanomolar, like I was speaking, nanomolar to picomolar range, we call it a stronger binding, and a weaker binding is when the Kd value is greater than micromolar, like 10 micromolar to millimolar range, we call it a weaker binding. Anything in between is a mediocre binding, or a very average binding. So lower Kd means higher affinity of protein for the ligand. Now these are a few examples of different proteins binding with the ligands and their different Kd values. Most of them are lies in a mediocre range, like 10 to the in the stronger region, like 10 to the power minus 12 to minus 8 Kd value. Okay, so like for example, you know about the receptor ligand interactions. So if you see from the color bars, you can understand that these lies around 10 to the power minus 8. So that's around 10 nanomolars. Okay, like then you have some sequence specific protein DNA interactions, like for the transcription factors, it's in the picomolar to nanomolar range, you're having a stronger affinity. Now the strongest interaction that's known is the biotin avidin, that is having around femtomolar affinity. That's the strongest binding known, right? So these type of interactions are very difficult to inhibit, and but they are very very important if you want a very stronger binding to something, like immobilizing some proteins on top of another. So these kind of interactions are very very helpful. Whereas you have some enzyme substrates, the proteins interacting with the substrate, they have a little bit of weaker binding in the micromolar range. Why is it so? Because at some point of time the enzyme has to just move out of that substrate, get out of that substrate after completing the reaction, or the reaction just keeps on proceeding. That makes no sense. So therefore, there are some interactions that are weaker, some interactions that are stronger. It is how we want to implicate our applications that we are using the different kinds of different binding pairs. Like for the enzyme substrate, we can use in different, so it has a very not a very stronger binding, but we can use in different applications where they will be where they can have higher benefits, right? So we have heard about the Gibbs free energy and how we can calculate the Kd value from the Gibbs free energy. So delta G equals to RTL and Kd, or RTL and Ka. So the sign can be neglected as of now. It is minus RTL and Ka, or RTL and Kd does not matter much as long as we are getting the value. And then So the binding constant can be connected with the Gibbs free energy by this particular formula, and the binding constant of Ki corresponds to the Gibbs free energy of 53.4 kilojoules per mole. So these informations are not very important. You need to keep this particular equation in mind, and that will do for this particular slide. Now it's just comparing about delta G, which is equal to minus RTL and Ka or Kd, you assume. And which is also equal to minus delta H minus T delta S. So minus delta G by T equals to minus delta H by T plus delta S. So you can improvise the equation in your own sweet manner. It depends on what you want to do, how you want to do, and that just does it. So this is all about the calculations, the formulas, and how we are, or what we are actually talking. It's about binding. Okay, we have talked about the different binding, the different proteins, ligands involved in different binding. There are the important types of protein ligand interactions, like they interact using some attractions or attractive forces, some forces or energies that allow these kinds of binding, like the hydrogen bonds, ionic interactions, hydrophobic interactions, cation pi interactions. So these are the forces that push towards the binding or any kind of attraction and all, right? So this is about what we want to get at the end of the day. Whatever we do, the binding is important. How can we understand whether the binding is tighter or not, whether what's the value of this binding, or how we can calculate the binding. So for that, Kd is important, the value of Kd or Ka is important, even what is delta G, what's the gives energy of free energy of binding. These informations needs to be collected if we want to talk about binding. But there still is a major question that needs to be answered. How do we measure it? Or what are the experiments, what are the instruments that we are going to use to calculate about the protein ligand interaction? How can we get it? That is a major question. So the next part will mostly include about the practical portion, where we will be talking about the different techniques, different instrumentations, where we will find out what type of or how can we calculate the binding or the interaction of a protein and the ligand. The first experiment is the isothermal titration calorimetry. It's not a very complicated technique. Rather, it helps you give a global idea about the protein interaction with the particular ligand. So what do you need to do over here? So the more or less the technique looks somewhat like this. So what does this technique measure? This technique measures the heat release due to binding. So over here in the image, if you see, so this is the probe that detects the heat that is generated. So you have basically two probes. One is the reference probe and the other one is the detection probe. In the detection probe, firstly you have the free protein molecules. And in the syringe, this is a syringe over where you have the ligand. So you are going to titrate it. So isothermal titration calorimetry. Why is it so? Titration because you're titrating the protein versus the ligand, or the ligand versus the protein. Why isothermal calorimetry? Because there is no exchange of heat from outside. Only whatever heat has been generated due to binding needs to be calculated. Now when you see over here that when there is a binding of the proteins with the ligand, some amount of heat is generated, and that is detected in the form of a graph. So isothermal titration calorimetry is a direct method. It measures the heat change associated with complex formation at a constant temperature. The complete thermodynamic profile of the molecular interaction can be calculated from this single experiment. This is very, very vital because this is the only experiment from where you can get the complete thermodynamic profile with high accuracy. The enthalpy, entropy, Gibbs free energy, from where you can calculate the binding affinity or the dissociation constant and all, and also you can get a large idea about the stoichiometry of binding. Like, what is the stoichiometry? One protein molecule binding to how many ligands, or one ligand binding to how many proteins. So there might be so many things that is happening. So there can be two proteins binding to one ligand, or two ligands can just go to and bind to one protein. So depending on what is the value of n, you can get an idea about the stoichiometry. So how does the instrumentation look like? Like I was saying, this is an adiabatic jacket, and you have a reference cell, you have the sample cell, the delta T is 0 over here. So this has a constant power to the reference cell heater, and the sample cell will actually release the energy upon binding. So the power supply to the sample cell feedback is kept at delta T equals to 0, such that whenever you are undergoing the titration, whatever heat is generated because of the protein ligand binding, that is actually finally detected. So when the detection actually occurs, how does it look like? It looks like this. So the curve is like this. So what is this? This is the delta P. So this delta P is the exothermic heat event that is occurring. So with time, there are more and more ligands. So there is a titration of the ligands. So more and more ligands are going and binding to the protein. So more binding means more heat energy released, or more energy released, and that is detected using this particular detector, like I showed in the first image. So this is the detector that basically detects the heat released or heat absorbed. Like when you have an exothermic heat event that is occurring, you get inverted curves, and when there is a endothermic event happening, so there are some positive curves. So depending on what you are getting, you plot a graph, and from there you can calculate the KD. So why is it going low and low at the end of these events? It is because there are, so like you have 100 molecules of protein, then you are titrating say 20 molecules of ligand at a time. So first one gives you a peak, the second one gives you a high, because there are firstly you have 20, first you have 100 free proteins, then you will have 80 free proteins, 20 complex, then 60 40, 40 60, and then it goes down to when there are no more protein left, and then we are just simply titrating the ligand, so it reaches a constant value at the end. So there is no more heat generation at the end, so the value goes down. So yes, this is what the titration calorimetry does. So you can, so this is a review of free energies, enthalpies, all thermodynamic parameters can be calculated from over here. So there is a convenient rule of thumb, that is 10-fold change in binding constant corresponds to 1.4 kilocalories per mole. So what do you need? So how many kilocalories per mole in free energy do you need to change KD by 100-fold? So that is, so we know ln KD 100, so log of 100, that will be around 2. So it is around 2.8 kilocalories per mole. So what I need to, so what is more important is that how does this instrumentation work that I have said? It measures the energy upon binding, the energy released, or the heat energy that is absorbed upon binding. Also, it gives you an idea about all the thermodynamic parameters associated with that type of protein binding, with the ligand, protein ligand binding. Another beautiful experiment is the SPR, that is the surface plasmon resonance. So surface plasmon is the longitudinal charge density wave along the two interface, where one is a metal and the other one is dielectric. So what is the principle behind this SPR, or the surface plasmon resonance? So SPR is excited by a plane polarized, totally internally reflected light at the glass or the metal film interface that you see over here, the orange line. The surface plasmon enhancing the evanescent field amplitude, that is E. Now it uses a sensor chip where the interface takes the form of an exchangeable gold coated glass slide, on top of which you have the protein that is on top of this. It's immobilized in this frame, in this film, and then you pass on the ligand. So it measures it measures the angle of reflection. So you see you have a sensor chip over here. These are your protein molecules. You flow through the ligands, and then you are calculating the angle of deviation. So you see the intensity versus angle. So there is a drop, and then again there is an increase, and secondly it happens. So when you're plotting it, what does k plus 1 indicate? So it's the on rate. So k plus 1 is the on rate. What does it mean? That the ligands bound to these protein molecules. So there is a binding that is happening. So first you allow, so the proteins are there, so those are free proteins. You allow the ligands to flow through them. So the ligands will get some time to bind to these proteins, and that is the on time. When it reaches a stabilization, it means that now all the protein molecules are bound to these ligands. Now comes the off rate, that is k minus 1. What does it tell? How quickly does these ligands actually get away from this protein? So if there is a higher binding, if there is a tighter binding, you will see the graph growing very slowly. So the slope actually gets decreases. But suddenly when you see that there is a weaker binding, the graph is like it goes very fast, the slope increases, and that means the off rate is very high. So based on the on rate and the off rate, we can get an idea about the binding affinity. So the physical applications of SPR measures the dielectric properties, adsorption processes, surface degradation or hydration of thin organic monolayers or bilayers. There are polymer films. Biological applications, like it can be used as biosensors for specific biological interactions, including adsorption and desorption kinetics, antigen antibody binding, and epitope mapping for determination of biomolecular structures, interactions of proteins with DNA, viral protein interactions, lipid bilayers, tissue engineering, non-specific biomolecular interactions, biocompatibility. Now, SPR has a few advantages, like its ability to perform real-time measurement, where you can get an idea about the dynamic nature of the binding system and layer formation, the on rate and the off rate. You can study the kinetics. That's very, very important. You can eliminate the need of labeled reactants, because you don't need to label this. So the price or the cost actually goes down, as well as there can be so many of harmful chemicals associated with it, so it does not require all those sensitive highly sensitive things, because it's already small quantities of purified reagents are actually required. So small amount of sample will just do it. You do not require a huge amount of samples. The disadvantages is that it lacks sensitivity when monitoring low molecular weight absorbents. The rate limiting factor of mass transport affects the kinetic analysis, and to improve this, it can be improvised by coupling it with AFM, that is atomic force microscopy, or mass spectrometry, so that can actually improve the functioning of the SPR, or the surface plasmon resonance. Okay. We will go into the third experiment, but maybe up till this much, if you guys have any doubt, you can just ask me. Any doubts from this portion of what I have said? Any questions? No questions, so I believe everything is clear. Okay, then let us go ahead then with the next experiment. So, what type of ligands are more prone to complex formation with proteins? So it is totally up to the function of the protein or the structure of the protein, the nature of the protein. It is completely different in different kinds of activities. So it's not like that the proteins are prone to one kind of ligands. There can be small molecules as well, for which some small molecules are cofactors for different enzymes, some proteins. Okay, there are some peptides that are used as inhibitors to bind to proteins to inhibit some kind of function. There are some transcription factors, like transcription factors are proteins that binds to nucleic acids, DNAs, RNAs. So there can be a wide variety of ligands. It's about the property of the protein and the function of the protein that it wants to attain that determines what the protein wants to bind to, which type of a ligand. Okay. So let us talk about the the third experiment or third technique, that is electrophoretic mobility shift assay, IMSA. So it's a gel-based assay or the gel shift assay. It's a technique to detect whether protein is attached with a DNA or RNA or not, and whether there are many cellular processes where a protein needs to interact with the DNA or RNA, like in a transcription and translation, like the transcription factors. Originally, they utilized broadly in investigation of sequence-specific DNA binding proteins such as transcription factors. IMSA has been additionally developed to explore DNA protein interactions, RNA protein interactions, and it's a very sensitive method because it uses radioisotopes to label nucleic acids and autoradiography. It is possible to use very low concentration and small sample volumes. So, like I will give an example, like the purified protein and the crude cell extract are usually incubated with 32p isotope labeled DNA or RNA probe, and the complex and the unbound probe is isolated on the non-denaturing polypropylene gel electrophoresis. Uh, Mobility shift assay is electrophoretic separation of a protein DNA or RNA protein on a polyacrylamide or agarose gel for a short period, and the speed at which the different molecules move determines the size, charge, and sometimes the shape. So like for a SDS page, it is moves according to the molecular weight. It is, but this in this case it's a native gel. So a native gel is a non-denaturing gel where your proteins are in the folded state, in the bound state, in the complex formation, and The mobility depends on the mobility will depend on the size, charge, and the shape. So how do we do it? So as we know that we are going to have a DNA interacting with a protein, and there needs to have enough DNA and protein in the solution. So your protein, so first you have a free DNA because the DNA is labeled over here, so you only see the DNA. So the DNA, this is the free DNA. With the increasing amount of protein, you see that the bound complex is also increasing. So first of all, we had so much where the protein concentration was maybe low, but as we increase the protein concentration, you see the bound fraction to be more. So how do you calculate the KD from here? By just looking at the gel, it is very easy to calculate, not very difficult. The point at which there is 50% of, like, you know about the amount of DNA band that you're seeing over here. So this is the free DNA band. So the point at which the band intensity gets lessened by 50%, that is approximately the KD value. Or you can just plot it in a graph and you can get about the KD. So it's the point at which 50% of the ligands are bound to the protein, that is your KD. So how does the gel look like? So it looks like somewhat like this, but there can also be super shifts, like you have the free DNA over here. There can be one band, and upon increasing the protein concentration or adding more and more protein, there can be two proteins that bind to one DNA. So there is another shift, we call it as the super shift. So the applications of EMSA includes conformational changes in the DNA, like an EMSA 2D variant with electron microscopy can be used for characterization of the conformation. Analysis of cellular extracts for the presence of certain DNA binding proteins. Bound and free DNA are separated using EMSA. It proves useful for stoichiometric analysis, number of protein that binds per DNA fragment. It is also used to study whether transcription factor is attached to the DNA or not, or if the transcription factor attached is a targeted DNA or not. EMSA has a few advantages, like it is used with a wide range of nucleic acid sizes, structure, as well as proteins. It's a relatively simpler method with qualitative analysis. It proves useful in detection of proteins that binds to DNA and causes difficulty in migration of fragments on a gel. It's a highly sensitive methods and usually at low cost, and very less amount of protein is actually required for these experiments. If your binding is tight, you do not have to use a lot of protein as well. And thirdly is that the protein needs not be very highly purified. It can be a crude extract as well, because your DNA is labeled, only you are tracking the DNA bound to the protein. However, IMSA has a few drawbacks. So it does not provide a straight away measure of the weights of the proteins, as mobility is influenced by all other factors as well. So you will not get an idea about the complex molecular weight. You cannot get an idea about the kinetic studies. Dissociation sometimes becomes a problem if you run for a long time. There can be dissociation if the buffer preparations and all are a little bit complicated. The next experiment is fluorescence and isotropy. So polarization in a fluorescence experiment. So you have an excitation along the x-axis and its detection along the y-axis. Anisotropy is preferred because the total intensity, it calculates the total intensity. So if you see over here that polarization states of fluorescence is described by P equals to the intensity across the parallel field minus perpendicular field, and divided by the intensity across the parallel field and plus the perpendicular field. Okay. Now for anisotropy, the thing is like R equals to intensity in the parallel field minus intensity in the perpendicular perpendicular field divided by total intensity. So intensity in the parallel field minus intensity in the perpendicular field divided by intensity in the parallel plus twice intensity in the perpendicular. So the question is, why does the total intensity equal to intensity of parallel plus 2 perpendicular? So if you see over here, you are exciting along a direction and it is the total intensity is detected along only the y direction. But actually there is also, when you're exciting along the x-axis, there can also be dissociation or detection, but there is not a detector over here. But had there been a detector, the you could also detect along the z-axis. So means the detection is only done along one particular axis, but it can also pass through the z-axis. So 50% of the intensity is actually lost. So 50% intensity goes into z, 50% goes into y, but you're only detecting along one direction, so therefore it's twice into intensity along the perpendicular, because you're not calculating along the z-axis, you're calculating only along one perpendicular axis. So anisotropy have considered frozen molecules. However, in reality, the molecules are mobile and their rotation changes the orientation of the dipole. So changes in theta are reducing the anisotropy caused by the photoselection. So for a spherical molecule, this rho is the rotational correlation time, and that's viscosity into velocity divided by volume divided by RT, which is equals to 1 by 6 times of the diffusion coefficient. For a globular protein, it's partial specific volume plus degree of hydration, and then there are so many factors. So these you do not need to keep all these things in mind. What you need to know is like what's the principle and how does it work. So you see over here the plane defined by the direction of excitation and detection is the XY plane, is called the horizontal axis, and the measured intensities are identified by the two indices describing the orientations of the excitation polarizer and the analyzer. So the polarizer is in the detection channel. So we have to account for different sensitivities of the individual polarizations. So R is your intensity across previously we had across the vertical axis minus the GIHV. So G is the set works coefficient across the vertical by the horizontal. So the calculations looks very complicated, but the experiment is not that. You have a protein, you add a ligand to it, and you get the different excitations at the different concentrations, and from there you plot a curve from where you can get the KD value or the binding. So polarization is suited to study the aggregation state of proteins. So one of them needs to be fluorescently labeled. So in the case of a protein dimer monomer equilibrium, following either intrinsic protein fluorescence or by labeling the protein with a suitable probe, one would expect the polarization of the system to decrease upon binding. So what is it actually calculating, or what is it actually doing? It is studying the rotation. Okay, so when you have the free protein, its ability to rotate is more. Now when there is another protein that is coming and binding to it, like a dimer or a trimer, the tumbling or the rotation of the complex, of the homogeneous complex, gets actually restricted, and that rotation or that particular change is actually detected over here, and then you are plotted. So you see the anisotropy is higher for the free one, and then suddenly it goes decreases because the rotation is somewhat restricted upon binding. Okay, any questions? Any questions from these two experiments? No questions? Okay. Then let us start with the question and answers. Right. So you people try answering, and then I will be discussing. Okay. So the first question says dissociation constant has a unit of concentration, concentration by time, concentration square by 10. What will be the answer? Dissociation constant. So how do you measure dissociation constant? So I just spoke about this in some slides. So the association constant has a unit of molar minus 1, and the dissociation constant is like 1 by Ka, that is 1 by molar minus 1, that is molar. So that is simply concentration. So option A is the correct one over here. Try to be a lot more interactive, okay? So try to give an answer. Maybe you will be wrong, but try to give an answer. I would be knowing that you are present in the class, because anyways I cannot see you guys. So but try to give an answer. Yeah. Okay, let's be interactive more. Electrophoretic mobility shift assay is a technique for studying DNA protein interactions. It is performed using agarose gel, native polyacrylamide gel, SDS polyacrylamide gel, urea polyacrylamide gel. Simple questions, quick answers. Yeah, I just spoke about EMSA experiment. What type of gel we use? Tell me. This is an easy question, so you all should be able to give an answer. Like, what type of gel do we run for an electrophoretic mobility shift assay? It is a native polyacrylamide gel. We cannot use an SDS because we do not want the complex to break, or a urea in a reducing condition, agarose gel, nothing can be used. We need a native gel where they will run according to like the size or the charge or something like that. So we want these proteins to be, or this complex to be, in the native form. So option B is correct. Which of the following experiments can be done to determine the binding kinetics under favorable conditions? IMSA, ITC, fluorescence anisotropy, or the surface plasmon resonance? Which experiments can you do to get an idea about the kinetics? Yes, absolutely. We can do surface plasmon resonance. Anything else? Option D is only correct. Yeah. The enthalpy of a binding reaction can be determined by. So enthalpy can be determined by ITC, fluorescence anisotropy, surface plasmon resonance, or IMSA. So I want to get an idea about the enthalpy. What experiment am I going to use? From which experiment do you get the thermodynamics? All the thermodynamic parameters can be calculated from one particular experiment. Yes, absolutely. ITC, isothermal titration calorimetry. So that will give you an idea about all the thermodynamic parameters. The free energy of binding can be determined from. So from where can you get an idea about the free energy of binding? So free energy of binding, that is delta G or delta G naught. Okay, I got one answer. Anyone else? So the trick over here is, how can you relate delta G? Delta G equals to minus RTLN KD or RTLN KD, whatever it is. So all these experiments can be used to get the delta G, because either you calculate the KD and get the delta G, or you get the delta G and you calculate the KD. So for all the experiments can be actually done. The next one, surface plasmon resonance detects change in heat after ligand is added to the protein, change in refractive index of the medium near the sensor chip, change in migration of the protein ligand complex, the change in the viscous drag. What does SPR detect? The change in heat after ligand is added, it is done by ITC. The change in migration of the protein ligand complex, it is also not true. Sometimes it happens in IMSA, or if it's about the movement, something like that, then the fluorescence anisotropy. You calculate basically the refractive index change of the medium near the sensor chip. So option B is correct over here for for question number 6. In fluorescence anisotropy experiment, a small ligand is stacked with fluorescent label. Which of the following is true? Increase in rotational diffusion of the small molecule is detected. Decrease in rotational diffusion is detected. The fluorescent label is excited by polarized light. It is excited by depolarized light. Which of it is true? You detect the polarized light or the depolarized light or the rotational diffusion. What is it that you are actually detecting? So there are two things that can be done over here. One is the decrease in the rotational diffusion of the small molecule that can be detected using fluorescence anisotropy. The other one is that the fluorescent label is excited by the polarized light that helps in the detection. Okay, the protein, so B and C both can be correct over here. The protein binds a ligand with association constant 10 to the power 6 molar inverse. What is the most likely measured KD in the presence of a competing inhibitor? So what will be the KD value in the presence of a competing inhibitor? Is it 10 to the power minus 5 or 10 to the power 5, 10 to the power minus 6 or 10 to the power minus 7? How will the KD value, what will be the KD value in the presence of a competing inhibitor? What does a competing inhibitor actually do? It competes with your ligand. That means it will weaken the binding, because sometimes it goes and binds, it will actually not allow the your ligand to go and sit over there, thereby the binding of your ligand with the protein will actually decrease. When the Ka value decreases, it means Kd value increases. So the only one where you can see that the Kd value is more than 10 to the power minus 6 molar, that is 10 to the power minus 5 molar. So option A is correct over here. You guys are not answering me. Okay, try to give me an answer. These are not very difficult questions. If you just think for a bit, you can answer, I believe. From the dissociation constant, it is possible to calculate what? The association constant, the delta G of the binding interaction, the concentration of the ligand required for half maximal occupancy of the protein, the binding on and off rates. So over here, more than one option can be correct. So which of them is? Yes, A is correct. Anything else? The association constant can be calculated. If you can calculate the association constant, or if you know the dissociation constant, you can also get the delta G. And when you know the delta G or the Kd value, from there you can calculate the concentration also, where there is half maximal occupancy of the protein. So A, B and C, all three can be calculated, but the on rate and the off rate cannot be commented, or we cannot comment on the on rate on the kinetics. We can only do that only when we do SPR. Okay. Now, in a titration experiment to measure the dissociation constant, the ligand concentration is varied and the protein concentration is kept constant. The ligand concentration is kept constant and the protein concentration is varied. It is necessary to determine the concentration of the free ligand, free protein and the bound complex. It is necessary to keep the temperature constant. So which of these are correct over here? In a titration experiment, which of these do you feel are correct? Over here, more than one option can be correct. So there can be multiple titration experiments where you have the protein and you're titrating the ligand. You can have the ligand and you are titrating your protein. So that's the reverse experiment. You can also do that. You have to calculate the free ligand, free protein and the bound complex. So to determine the KD, you need all of that. Okay. But to calculate the KD, you need the bound fraction. Okay, and you need to keep the temperature constant, because after all delta G equals to RT, where T is constant. So all the options are correct over here. The next example is the next question is EMSA, or electrophoretic mobility shift assay, is used to study protein small molecule, protein nucleic acid, protein protein, or protein polysaccharide interaction. What do you do EMSA for? Protein small molecule, or nucleic acids, or proteins, or polysaccharides? What type of interaction do you track in IMSA? These are easy questions. People should be able to answer. Yeah, for IMSA we do a protein nucleic acid interaction. You fluorescently tag the nucleic acid and then you run a native gel to understand the complex. So a protein ligand complex dissociates with an off rate of 1000 second inverse. What is the time constant for this reaction? Is it 1000 seconds, 1 second, 1000 millisecond, or 1 millisecond? How will you calculate the time constant? So time constant can be calculated as 1 by k off. So 1 by 1000 seconds. That is how much? 10 to the power minus 3 seconds, 1 millisecond. Yes, option D is correct. Okay. The expected off rate of a protein ligand complex is 100 second inverse. Which of the following is true for the experiment designed to study the kinetics of this reaction? Data should be collected at every 4 milliseconds or faster. Data should be collected at every 40 seconds or faster. Data should be collected for at least 40 milliseconds or longer, or data should be collected for at least 400 seconds or longer. So the K off rate is 100 second inverse. So in order to study the kinetics, you see 1 by k off, that is 1 by 100. If you do, that is 10 milliseconds. So you have to do somewhat like 4 milliseconds or faster. So data should be collected every 4 milliseconds or faster, because the off rate is 100 second inverse, and it should be collected for uh, around 400 seconds, like if for you to get multiple data points. So A and D both are correct over here. Yes, A is definitely correct, but you should, if you want to collect the data, you should do for 400 seconds or longer to see if all the molecules have so 100 second inverse, if that is the dissociation rate or the K off rate, then you have to calculate for 400 seconds or longer. For protein ligand interactions described above, which experiment is or are suitable to study the kinetics? So for the above mentioned experiment, which of the experiment is suitable for calculating the kinetics? Which experiment will give you the kinetics of this particular reaction? So the kinetics can be, so the binding kinetics, the K on K off rate can be easily calculated from the SPR, or the surface plasmon resonance. Okay, so you can get the kinetics using when you perform SPR. So there is an on rate when the ligand is binding to the protein, and when you're washing it, the ligand is opening or dissociating from the protein, you calculate the off rate. So SPR. Now, last question, ligand A and B bind a protein P with dissociation constant of 1 nanomolar and 100 nanomolar. Which of the following is true? A binds P more tightly, B binds P more tightly. A has faster off rate, B has faster off rate. So it is said that the Kd value of A to P is 1 nanomolar and B to P is 100 nanomolar. So which of the following will be true? Which of the options do you feel is correct? So what does that mean? Lower the Kd value, higher is the binding affinity. So if the Kd value is low, that is 1 millimolar is less than 100 nanomolar, 100 times less Kd value, so A binds P more tightly. Okay, so the correct option over here is A, not B, because the Kd value is 100 nanomolar for B to P binding, but for A to P binding it is 1 nanomolar. So lower Kd, higher binding, higher Kd, low binding. Okay. Okay, two more questions. Right. So I have two more questions. Okay, let's see. Ligand A and B binds a protein with dissociation constant K of 0.001 second inverse and zero point 0.1 second inverse respectively. So the K off rate is given. For A and B, association rate constant is 10 to the power 4 molar inverse second inverse and 10 to the power 7 molar inverse second inverse. Which of the following is true over here? A binds P more tightly, B binds P more tightly, complex is longer lived than BP, or BP complex is longer lived than AP. So you know the K off rate and you know the K on rate of the following reactions. So when you know the K off rate, let us first focus on the on rate. So A binding to P and B binding to P. So you see the association rate constant is 10 to the power 4 versus 10 to the power 7. So B has better K on rate. So B binds P more tightly over here, right? Because the K on rate is good. But if you see that the off rate, that is for A, it is around 1000 seconds, and for B it is around 10 seconds. So AP complex is longer lived than BP complex. B binds P more tightly. From the K on, we can tell which binds which more tightly. But from the off rate, we can tell the complex is longer lived. Which complex is longer lived? So from here we can tell that AP complex is longer lived than the BP complex. Okay. And last one is the dissociation rate constant K of protein DNA interaction is determined by EMSA. The intensity of the free ligand can fit to which of the following equation? I equals to I naught 1 minus e to the power minus k of t, or plus e to the power k of t, or e to the power k of t plus e to the power k of t, or minus e to the power k of t. Which will be the correct one? So it is simple, like you know the equation I equals to I naught e to the power minus. So there are so many equations where it is like e to the power minus kt. So you know that one of the e to the power, that is minus k of into t. So I equals to I naught 1 minus e to the power minus k of t. So that will be the correct option over here. So if you need to fit your equation into this ligand, you will have to calculate the final intensities, that is the complex intensity over there and the free intensity of the protein, of the ligand, that is fluorescently labeled. So you calculate the two intensities and fit in the curve, you can get an idea about the k off rate as well. Okay, yeah, any questions? Any questions from anyone? Because I am done. Yeah, I am done from my side. If you have any questions, you can ask me. And I will be sharing the video as well as my slides with the NPTEL team. They will be sharing with you. So I believe no questions. Okay, if you have any questions, you can ask me in the next class, early half of the next class. If that is so, thank you very much for joining. We will meet again in the next week at 6 o'clock, Friday.